Okay, I'm going to demonstrate a test that I made to check internal resistance on 18650 cells. And here's the hardware, the test setup. We have a Samsung cell that's connected to the electrodes are connected to the testing system, which consists of a resistive load and an Arduino Uno and an ADS1115 analog to digital converter and a relay, basically. So what happens here is that during the test, the analog to digital converter collects voltages in the open circuit for 5 seconds. Then it switches on the load, and the load stays on for an additional 10 seconds. And the system sends that data at the rate of 5 determinations per second over to Excel. And then at the end of the test, Excel calculates the constant rate of voltage decline in the last 5 seconds, extends that regression line out to the point where the load was connected, and then we have the voltage drop between the open circuit voltage and the voltage across the known resistance that was observed. And then from that we can calculate the internal resistance, which I'm calling the no load resistance, because it also includes other things like contact resistance, the constant discharge rate at the end, the total power that was available, and the percent loss, that is the percent of the total power that did not go through the resistive load that was consumed by the cell itself and also by any contact resistance. Now here the result, that incremental loss apart from the cell is 0, because we have put in there a previous value for this cell that the connections on this cell are the nickel strips that were factory installed in the stack that I purchased, from which I harvested this particular cell along with 40 others. So this is measuring basically a baseline for the recommended way of attaching cells for packs. So that's what we have. Now, to run the test, what I'm going to do is just basically click up here to connect, and what you'll see happen here is temporarily the screen goes blank. Now it turned on the resistive load, and then after 10 seconds it will turn off the resistive load, and we'll see the results for the cell. So it's off, and now we see the results for this cell. So we see the other one was 62.4. This time we got 62.2 for the same, essentially the same thing. And as we look over here, there still is no incremental loss beyond the internal resistance of the cell. The total loss was 3.8%, and it was 9.3 watts that were generated altogether. So we'll just leave this as is, and then I'll substitute a cell in a battery holder, which should not be, it should show more loss in terms of beyond the internal resistance of the cell itself. Okay, now here is the second test that we're going to do. This is a cell from the same pack, and previously tested with the factory installed nickel strips still intact. It was identical to the cell that we just tested. So here it is with the nickel strips removed and now in a plastic battery holder. And what I've done is to solder on nickel strips to the connectors in the battery holder at the top. So this will simulate, in terms of the connection itself, what we just did, but instead of spot welded connectors, this is just touching the connectors in the battery holder. So now we're going to go ahead and run this one and see what we get. So I'm going to come over here and reactivate it. Okay, so now it's been reactivated and the screen goes blank until we collect the data. It's doing the first 5 seconds. Now it turned on the resistive load, and after 10 seconds it will turn the load off, and then we'll see the results. Okay, so here's the results, and what we see is now the total resistance, that is the internal resistance, which would have been around 62.4, plus the added resistance of the contact in the battery holder, comes out to a total of 73.1. Still have 9.1 watts, but now we have a 0.7% additional loss, which I'm calling an incremental loss beyond what we would have seen in the spot welded cell previously. So that's essentially how the test works. Now when I first started working on this, I just used a voltmeter, and the problem that I had was when I turned on the load, I was seeing not a constant result but a constantly changing result, and it was difficult to know where to pick the value for the voltage drop. And you can see here that if we go over to this point, there's a gap between what the voltage drop should be and the way it appears if you pick when it first starts changing. So if you were to do that, you would underestimate the voltage drop. If you, like I've seen suggested, if you wait 5 seconds and then pick a result, that would bring you over here to 10 seconds. And if you bring that line back over, you would overestimate the voltage drop. So what I decided to do here is wait until the change in voltage over time became constant. That is, when the cell is producing power at a constant rate. Initially, when you first engage the load, I think there's some stored charge that's in the cell, sort of like a capacitive effect by analogy. And after that's been dissipated, then at some point the cell starts generating electricity at a sort of an equilibrium rate, and that we can get through a regression equation in the last 5 seconds out here, and then just extend that line out to the time when the load was turned on, and then if we bring that back over to the y-axis, we can get the voltage drop more accurately and more reproducibly. Okay, now switching this to another holder here. It's the same type of battery holder, and by the way, I believe that the connectors in these, since they're slightly magnetic, only very slightly magnetic, are probably something like 302 stainless with a nickel coating. If you were to just use stainless spring clips like this, they tend to develop a surface coating that increases contact resistance. So these I think are probably nickel coated 302 stainless or something like that. Anyway, what I've attached here to the anode end is I have a connector on here. See if I can show you that on the side that's connected. It's a nickel strip that's connected directly to the anode. Then I have one up here that's connected to a 4 amp fuse. I have one down here that's connected to an 8 amp glass fuse, and then I have this PTC that's connected instead of these. So what we can do is put the same cell in here, and we'll measure it in the holder as is, and then we'll measure it through as the current is flowing through each one of these, and see what the losses associated with that in terms of power losses are. So this is the same cell that we tested previously, and first we'll test it with the electrode connections directly to the battery holder without any of the fuses or the PTC in the circuit. Okay, so we'll see what we get. And Okay, so there we started the test. And now it's turned on the load. You probably heard the click of the relay. And there it turned the load off. So we got about the same thing we did last time in the other battery holder, 70.6 and a incremental loss of 0.5%. I think the other one was 0.7%. Okay, so now I'm going to shut this off, and then we're going to do, I think we'll do the 8 amp fuse first. Okay, so this time we're connected to the 8 amp fuse, I believe. So we'll see. I could have gotten the fuses mixed up, but at any rate, we'll see here what happens. So I'm going to click this back on, and we'll do another test here. Okay. All right, that's done. Okay, now what we see here is with the 8 amp fuse in there, we went from 0.5, let's see if I can zoom this in a little bit. We went from 0.5 up to 1.5%. So that was the 8 amp fuse added an additional 1% loss in terms of power. So in other words, that extra 1% is being dissipated in heat from the current flowing through the fuse itself. And so now we're up to 87.1 milliohms of resistance total, including the internal resistance, which was around 62, and the extra resistance of the fuse. Okay, now so next we'll do the 4 amp fuse, which 4 amps is going to blow at a lower current. So that one is probably a thinner wire in there, and probably will show more resistive loss. Okay, so now you can see we're connected over here to the 4 amp one. At least I think that's the 4 amp one. So we'll come up here and run another test. There's the mouse thing. Okay. Okay, see what we get here. This is again the first 5 seconds to establish the no load voltage, and now the load is clicked on, and it waits 5 seconds, and then it'll use the last 5 seconds worth of data to do the regression equation. Okay, and well, I think I had them reversed. Okay, so this one, it turns out, is the this one is the 8 amp one, and we see that there's less of a loss there. So we went from 0.5 to 1 for the 8 amp, and then when we go to the 4 amp, we go to from 0.5 to 1.5. So each one of those fuses is increasing another 0.5%. So, you know, the reason that this is significant is those, you have to, I guess, factor that loss in when you're deciding, do I want to use fuses on each cell? If so, here's the loss that I'm going to see. And if I use 4 amps versus 8 amps, it's the kind of a difference that will be associated with that. So next we'll look at the PTC. Okay, so here we're connected to the PTC, and we'll just go ahead and test this one. And see what we get. Okay, and now this one, the PTC is quite a bit more loss. So we went from 0.5 initially with the factory spot welds up to 2.2% loss. We're still at about 9 amps here. As we drain the cell, we're going to, you know, the amps is going to go down a little bit gradually, but we're up now to 90, I don't know if you can see that, 98.3 milliohms, when with just the factory spot welds we were down at 62. So I was originally thinking about using these PTCs. They're resetting, but as Micah Toll pointed out to me in a comment, why would you want to reset the system for a cell that's going bad and is bad enough to trip the fuse? Why? And this thing cuts out at 8 amps, but it's very slowly. It's like takes several seconds for it to fail, and then you wouldn't want to reset it anyway. So if I'm going to use fuses, I'm going to use the pigtail glass fuses. Okay, now the next one I'm going to do here is the Bruise End Connectors, which are, I guess, relatively new. These have a contact that looks like this in the holders, and you can link them together like this to make packs. So the nice thing about these, at least the concept of these, is that you could use these cells to make a pack with no heat added, not even the heat from spot welding. And more importantly, if you want to take it apart and use the cells in another configuration, no problem. It's easy to do, and even with spot welding, it's problematic. You know, you got to peel off the nickel strips, then you'd have to re-spot weld them, and every time you do that, you're changing the heat history, you're adding to the heat history. There are nickel organometallic compounds that build up as a result of that increase internal resistance. What I've done here is to take these nickel strips and use a brass washer and the supplied nut to attach the nickel strip directly to the bolts that are provided. This is all stainless steel. This is totally non-magnetic. I doubt if it's nickel coated. So anyway, let's see what we get with this. Okay, so we just connected the load. Okay, so here's the result. 1.7% incremental loss, 91.1. So let's do that again. And 90.8, 1.7% incremental loss. Okay, now this time I'm using the supplied stainless steel bus bars and the stainless steel nuts on both ends. So same cell, so we'll see what happens this time. Okay, now you see we're up at 5% loss and 147.6 milliohms, just due to that's the total. So 5% loss, incremental loss, due to the connection system alone. Okay, so I'm going to repeat this. I repositioned the clips on there just to see what that does, if anything. Okay, now we're at 213. So my guess is that this, and now we're up to 8.6% loss. My guess is that that we're having a contact resistance issue, possibly here or both. And of course stainless steel is quite low in both thermal and electrical conductivity compared with, you know, copper or even aluminum. So, but this is a very short distance, and I doubt if it's the bulk resistivity of the bus bar that's responsible. It's probably contact resistance. Okay, so now I'm going to use the brass or bronze strips that are intended for the final high amperage takeoffs for the entire pack, but instead I've put them on an individual cell here to see how the results compare with the stainless steel bus bar that we just looked at. So here we go. So now we're at 2.7% incremental loss compared with the spot welding, and up to 107.4 milliohms total. So, and again, you notice the total power continues to decline a little bit because we've tested this cell over and over again, and the state of charge is decreasing as we do that, but nonetheless these percentages would still be applicable. So, and by the way, the internal resistance does remain stable over a wide range of state of charge. It's pretty flat, so it's not affected by state of charge. Okay, and now I'm going to return to one of the cells that I have that has the factory spot welded strip still attached and retest it. Okay, so we got 59.9. I think last time we were around 62, so could be a little difference in terms of how the clips are attached. Could explain that, but it's still quite a bit lower than, you know, the other things that we've been testing here. And we'll check the 8 amp fuse again. That's that one. Okay, so it looks like 0.8% above the, at 76.2 milliohms, 0.8% extra loss above the thing, and that would include the battery holder as well. So I'll just check the battery holder again real quick too. Okay, so this one we're redoing just the battery holder without the fuses. Okay, and we got 0.4 just for the battery holder. So we got 0.8, so it only went up 0.4% with the addition of the fuse. 0.4% for the battery holder, 0.4% for the fuse. So now here's again the 4 amp fuse. This one should be higher because it's a thinner wire, so should have more resistive loss. And it is 1.4%, so it went from 0.8, so it picked up another 0.6%. And, you know, there's some error in the test, so figure about, like we got before, about 0.5% for the 8 amp, and about another 0.5% added on to the battery holder at 0.4. So that all checks out when we retested it. So in closing, what makes this possible is a piece of software that was originally called PLX-DAQ that allows transfer from a device like the Arduino via the serial bus to Excel. And it was originally put out and made available for use for free, basically, by a company called Parallax Inc. that I believe is into robotics, and also in cooperation with Selma Software Solutions. Selma, I think it's called Selmaware Solutions. Subsequently, that was, I think, in 2014, if I'm not mistaken. That was then rewritten by somebody on the Arduino forums who goes by the name NetDevil, and this individual lives in Stuttgart, Germany. Did a great job rewriting it so that it works with Windows 10, 60 and 64-bit also, and he also made it open, sort of open to modification by users. So I've added a few routines to the ones that extra ones that he provided, and that's what makes it viable in this particular application. In this case, I'm only transferring data from the Arduino to Excel, but it can work the other way as well. And I'll put a link to this, to NetDevil's modification. You can download it for free. And it's a link to the Arduino forum in case you're interested. Okay, the other thing I should mention is that you can do this without the graphs and without all this stuff. You don't need any of this. You could really do the same thing with a timer and just a voltmeter like this and a timer. So, and of course, the one thing you do need is you need to have the load. So, what I've used here is two 3-watt, 25 watt, 3 ohm resistors in parallel. So, and this, by the way, I checked this out with a lab power supply, supplying the voltage and measuring the voltage in amperage, all the way from 25 degrees C up to 55 degrees C, which is 130 F or so, and you can't really touch it, it's so hot at that point. And the resistance calculated from those voltage and amperage measurements is very flat, it's stable. So this isn't really affected by temperature. That's what this thermocouple is on there for, is that study that I did. I decided to just leave it connected in case I ever want to check the temperature, but it's, especially in this kind of a use where it's on just for 15 seconds at a time, temperature is not an issue at all. So anyway, the way you could do this, as long as you have a load like that, is basically you'd start a timer and then you'd hook your voltmeter up to prior to the switch that goes to the load. You'd hook your voltmeter up and just write down the voltage in the first 5 seconds, and then when you hit 5 seconds, you'd switch on with a push button or something. You could, any kind of a switch, switch on the load, and then wait for 5 seconds, and then you would take the voltage at the 10-second mark. So you started at you started at 0, then at 5 seconds you switch on the load, and you take voltage reading at 10 seconds and at 15 seconds. So you're going to get a decline in voltage between 10 and 15 seconds. That would be, in this part of the graph. And then all you need to do is you figure out what that decline in voltage is and just add it to the reading at 10 seconds, and you'll wind up with this point here. So you don't need to have a regression equation or anything like that, or Excel or graphs. You just take the reading at 10 seconds and the reading at 15 seconds, take that, whatever the size of that drop is, and add it to what it was at 10 seconds, and you'll have the reading at 5 seconds, which is where you switched on the load. So if you do that, you can then do the rest of the calculations manually or however you want to do it to wind up with the same results.